Welcome to the Dupe Dive. So today we're looking at something that I'm sure you've almost certainly experienced, but you probably, just dismissed it as an illusion. It's about the astonishing way sound travels when the temperature really drops.
Oh, absolutely. If you live anywhere with a real winter, you know exactly what we mean. That distant train whistle or even conversations from way down the street, suddenly they're just sharp and clear.
Right, almost like they're amplified.
Exactly. And it's not just a trick of your mind.
Yep.
It's definitely not magic.
That is the mystery we are cracking open today. We are taking a deep dive into the physics of how low temperatures fundamentally warp sound waves. We're focusing on a concept called thermal acoustic refraction.
Yep.
And our mission is pretty simple: to stop guessing why cold air changes sound and actually understand the science that turns your neighborhood into a kind of acoustic superhighway in the winter.
And the core idea here is genuinely surprising. It's that layers of temperature in the atmosphere can literally bend sound waves. We're going to show you how that bending process keeps the sound energy focused right on you, the listener.
Okay, so let's unpack that word, bending. The idea of refraction. I mean, we usually associate that with light, right? The classic example of a straw looking broken in a glass of water. So what's the fundamental principle there, and how does it apply to sound moving through air?
Well, refraction, at its core, is simply the change in direction of a wave. Any wave. It happens when its speed changes.
Okay, when its speed changes.
Exactly. With the light in water, the speed changes because the medium itself changes from air to water. But for sound, the medium is always air. It's just that the properties of the air, specifically its temperature, are creating these different layers.
So what you're saying is the atmosphere itself has these invisible sheets with different resistance levels that the sound has to push through.
That's a great way to put it. And here's the crucial detail. Sound actually travels faster in warmer air.
Wait, okay, hold on. Let me just challenge that for a
That's
second.
funny.
Because my first thought, and I think a lot of people's first thought, is snow. And so muffles sound.
It does.
And cold air feels dense, it feels still. So common sense might suggest that cold air should dampen sound, not make it travel farther.
That's a fantastic question, and it really gets to the heart of the physics. The snow muffling you're talking about, that's absorption. The porous snow surface is physically trapping the sound waves. That's a totally different mechanism.
Hold
We're
on.
just talking about the air itself. And when air is cold, the molecules are packed tighter. It's denser.
Okay.
But, and this is the key, the speed of sound is all about how fast those molecules can bump into each other. In colder air, they're sluggish. They move slower.
So fewer collisions per second.
Fewer collisions, which means a slower transfer for the sound wave. So
Right.
cold air is a slow medium for sound.
And on a typical cold morning, you get that temperature inversion near the ground, right? The ground is colder than the air just above it.
Precisely. That thermal gradient. The air right next to the ground is extremely cold, and so it's very slow. But just a few feet up, the air is usually a little warmer, so it's a slightly faster medium.
So you have a sandwich, fast sound on top, slow sound on the bottom.
You do.
Okay, this is where I need that crystal clear analogy. How does that gradient make the wave physically turn downwards? It's hard to visualize.
Let's use a simple metaphor. Imagine a big rolling wheel.
Okay, got it. A wheel.
It's rolling along a road, and one side of that wheel suddenly hits a patch of thick mud. That's our slow medium.
Right. And the other side is still on the pavement, the fast medium.
So what's going to happen?
Well, the side in the mud slows way, way down, but the side on the pavement keeps going full speed. So the whole thing, it has to turn. It pivots toward the mud.
Pivots toward the mud. And that is exactly what a sound wave does.
Ah, okay.
The top part of the wavefront is in that slightly warmer, faster air, so it's pushing ahead.
Right.
And the bottom part is getting dragged back by the cold, slow air near the ground.
So the faster top section is constantly pushing the whole wave front downwards. It's steering it back toward the earth.
That is thermal acoustic refraction in action. Instead of the sound just going up and dispersing into the atmosphere, it gets trapped. It gets focused along the surface.
And this is where it gets really interesting for us, right? The so what?
Right.
This focusing effect isn't just a tiny adjustment. It completely changes how far sound can travel effectively.
Completely. The atmosphere is creating what is essentially a natural acoustic waveguide. All that energy that would normally be lost going upwards is now channeled and preserved. It doesn't have to fight dissipation over distance nearly as much.
So the air is literally delivering the sound horizontally, which maximizes the chance it reaches a distant listener. That explains it. That's why the car door slamming 2 streets over, which you'd never hear in July, Sounds like it happened right outside your window in January.
It's the acoustic equivalent of shining a flashlight straight up versus shining it straight ahead.
Right, one disperses, one stays focused.
And when the atmosphere bends that beam of sound down, it keeps it tight along the surface. This is why, as our sources noted, you suddenly hear your neighbor's conversations or a truck miles away. You're not trying to eavesdrop. The sound is just being delivered right to you.
Okay, let's move from anecdotes to the hard proof. Because this isn't just a feels-like thing. Scientists have actually quantified this.
Oh, it's very well documented, yeah. One of the most compelling bits of evidence comes from studies analyzing sounds from trains or other consistent sources.
And what did those studies find?
They found massive increases in range. Specifically, some studies recording train sounds in winter showed that the sound's effective range was doubled.
Doubled.
Doubled compared to its normal distance under warmer conditions. Just think about that. Doubling the distance means covering 4 times the area.
4 times the area.
Oh.
That's exponential. That's not a subtle effect at all. It basically validates every single time you've stood outside and thought, I can't believe I just heard that.
Absolutely. And this had real-world significance long before we had modern sound equipment. Militaries have, probably unintentionally, relied on this for centuries.
You mentioned soldiers hearing battles from impossible distances. Tell us a bit more about that context.
Well, before radio, what you could hear was vital battlefield intelligence. And in the cold climates of, say, European winters, soldiers would report hearing cannon fire or troop movements from ranges that would have been completely silent in the summer.
Wow.
They were benefiting from the atmosphere acting as this huge natural listening device, just channeling all that sound energy right along the frozen ground.
It must have seemed almost supernatural, this sudden boost in awareness just driven by a temperature change.
It really does alter the sensory boundaries that we assume are fixed. We just take for granted how sound behaves. But this proves that simple temperature gradients can completely restructure those rules.
So to summarize our deep dive here, when the air is cold near the ground, it slows sound down. The warmer, faster air above pushes the wavefronts down, bending or refracting the sound. And that channels the acoustic energy along the surface, which massively increases how far we can hear.
That's the takeaway. It's a powerful reminder that these simple, invisible shifts in the atmosphere can completely govern the physical laws operating right around us.
This brings up a great final question for you to think about. Our sources mention that cold weather doesn't just refract sound, it also, quote, electrifies the atmosphere. So if a simple difference of a few degrees can double the range of sound, what other physical phenomena, from static electricity to maybe even how smells travel, are being radically altered around us by these constant, invisible temperature changes?
It makes you realize the world is far less static than it appears. Every time you step outside, you're in an environment where physics is constantly in flux, transforming the very way we perceive everything. Next time you hear that distant whistle on a cold day, you'll know. You're not just hearing a sound, you're listening to atmospheric physics at work.